Hello, Year 11. Welcome to the fifth lesson for exercise 10F, sum and product of zeros. Now this is, as I said, the only new stuff that you will see in Year 11, as the other things are meant to be Year 10 5.3 revision. So this exercise aims to link the coefficients of a polynomial to the zeros of the polynomial. So when I say zeros, I hope you guys remember the definition. It's the solutions to the polynomial when it's equal to 0. So let's consider a quadratic first, because that's the easiest, and then we will extend the idea to cubic and quartic. But let's say we have a quadratic ax squared plus bx plus c. Then my a, b, c are my coefficients, and let's say that it's got solutions alpha and beta when it's equal to 0. So knowing those two things, first of all, when they say zeros, I'm solving for this expression is equal to 0. And if I know that my zeros will be called alpha and beta, I know that the equation will be factorized to that version, as in it'll be bracket x minus whatever alpha is, and then another bracket x minus beta, whatever beta is. Now we are going to link those two together, but this one is actually a monic polynomial. If you expand this out, I get x squared minus alpha x minus beta x plus alpha beta is equal to 0. It is a monic polynomial, and this one is non-monic. So let's try and match them together so it looks like a monic. So I'm going to divide everything by a. Now it's going to become x squared plus bx over a plus c over a is equal to 0. Now on the right hand side, I'm actually going to factorize these two together so it looks similar to this equation. So we're trying to match the two equations look similar. So for this one, I'm going to factorize it as x squared minus alpha plus beta lots of x plus alpha beta is equal to 0. So I've actually done two things. First of all, I expanded it to make it a trinomial. There's 3 terms here and 3 terms here. And I've also made both of them look like a monic polynomial. And that's because if they are in the same format, I can now equate the coefficients. So have a look at this form and have a look at this form. We are now going to match the coefficients. First of all, I don't need to look at the coefficient of x squared because they're both 1. But if you look at the coefficient of x in this expression and this expression, I can pretty much conclude that b over a should be the same number as negative alpha plus beta, because we actually started off with the same polynomial, just written in 2 different forms. And if I can say that, I can make alpha beta as a subject and say alpha plus beta is equal to negative b over a. And that is actually the first identity for sum and product of zeros. Did you notice how we actually have a sum of zeros? And the title says sum and product of zeros. So we've actually just derived the first identity. The sum of zeros is in fact equal to negative b over a, where b is the coefficient of x and a is the coefficient of x squared. So without having to find the zeros separately, I can now find the sum of the zeros looking at the coefficients of a polynomial. So I don't have to solve anything. Now for the second identity, let's compare the constants together. So the constant on the left-hand side is c over a, and the constant on the right-hand side is alpha beta. And knowing that they're the only constants in the expression, I can say that C over A must be the same as the constant over there. So then again, writing down the zeros as my subject, we can conclude that the product of the two zeros is equal to C over A, which is the constant in the expression divided by the leading coefficient. So again, without finding the zeros separately, we can find the product of the zeros based on the coefficients of the polynomial. Okay, and that is what I've written in the orange box, so you don't really have to copy them down again. Now these are the identities you have to memorize for a quadratic. We can do the exact same thing with a cubic, but there's just a lot of algebra stuff going on. So have a look at this generic expression for the cubic and the generic expressions for the zeros of the cubic. And we'll do the same thing. When we talk about zeros of the polynomial, we are letting that expanded expression equal to 0. And for this one, given that the zeros are alpha, beta, and gamma, we can make it into factorized version like so. Let's expand the right-hand side first. So if I expand the first two brackets, we will get x squared minus alpha x minus beta x plus alpha beta times x minus gamma. And then if you expand out everything, you will get x cubed minus gamma x squared minus alpha x squared plus alpha gamma x, gotta be careful here, minus beta x squared minus beta gamma x plus alpha beta x minus alpha beta gamma is equal to 0. Now let's just count. I should have 8 terms because it's 4 terms by 2 terms. 1, 2, 3, 4, 5, 6, 7, 8. I think that's correct. And then I want to collect it so that the cubic terms are together, the quadratic terms are together, and the linear terms are together, and so on. So let's just highlight. There's my cubic term. That's the only thing. My quadratic terms are here, here, here. My linear terms are here, here, and here. And ooh, actually I can spot an error. This one has to be positive. And then my constant term is this one. So then now I can factorize all the coefficients together and say it's x cubed plus, nope, let me factor out the negative as well, minus alpha and beta and gamma, lots of x cubed, x squared, plus it's alpha beta plus beta gamma plus alpha gamma, lots of x, minus the constant. Phew. Now on the left hand side, the only thing I have to do is to make it look like a monic, like this one over here. So I'm going to divide everything by a. Notice how you see a bit of a similarity. We're always going to get the b, c, d over a. And then this one, let's see if we can find the pattern. So if we equate the coefficients, let's just bump that up to the top. We will get, firstly, let's compare the coefficients of the x squared. So that one versus this one. I can say that alpha plus beta plus gamma has to be negative of BA. So this one's actually the same as before. Remember the previous identity said the sum of zeros had to be negative B on A? Same start. And then the next bit is where it gets a little bit weird because I see C over A and I've got this weird expression. So we're saying alpha beta plus beta gamma plus alpha gamma is equal to positive C over A. So the C over A bit is similar to the previous one, but instead of having a product of roots, I get a weird expression. This one, if you actually have a look, is the sum of pairs of roots. They're all the different combinations you can get for pairs of the roots. And we often call them zeros in pairs. So let me actually label each identity as I go. The first one, this one was just sum of zeros in singles. And then this one is a sum of zeros in pairs or in twos. And then the last one, if you compare the constants together, I guess this is the same bit as before, but instead of having the C on A, we now get negative D on A. And this one, you could say it's actually a sum of zeros in threes, but there's only one combination like so we can just call it product of zeros. But really, it's just the singles, doubles, and triples, pretty much. And this, guys, is the identity for a cubic polynomial. As you can see, it's very hard to derive, so you can just, not that you can, you should just memorize it as they are. If it's confusing, you need to sort of find the patterns by yourself. So as I said, it's always going to be sum of singles and then doubles and then a triple, which is going to end up being a product. On the right hand side, we will always start with negative B on A, and then you can see it goes in order. It's C on A, D on A, but the sign always starts from negative, goes to positive, and then to another negative. So it's the signs are actually alternating as we go down the identity. And we could derive the same thing for a quartic. So that's a summary of the cubic, but we could do one for quartic, but nah, I don't want to do it. Just look at the summary and memorize the identities. But you should see the patterns again. See how we always start with the sum of zeros? We've got alpha, beta, gamma, and delta, which is always equal to negative B on A. And then you've got the sum of roots or zeros in pairs. So those are the paired combinations you can find between alpha, beta, gamma, delta. And it's equal to positive C on A. Now we've got 4 zeros, so we can find the sum of zeros in triples. There are 4 different combinations, which is going to be negative D on A. See how the signs are alternating? And then the last one is meant to be the sum of zeros in 4, but there's only one combination. So it's a product of zeros, which is equal to positive E on A, where E is the constant in this case. So there's definitely a pattern that you can see. And if you know that pattern, it's going to be easier to memorize the identities. As far as I remember, I think on the reference sheet, there's only ones for quadratics. It's very rare that you'll get a question on quartic. So really, the only thing you better memorize is the cubic one, which are these ones. So yeah, if you do enough questions, you should be able to memorize it. So let's try example 1 together. It says, show that negative 6 is a 0. That one's easy, because we just have to sub it in. No, it's not going to let me change my color. Nope, it's not going to make me change my color. Please don't do this to me. I don't know why this happens. Maybe if I play around with it, it's gonna, nope. Maybe if I try typing something. It works. I found the sorcery. Okay, part A. To show that it's a 0, we just simply have to sub it in to show that it equals to 0. Sub it in, sub it in. You just chuck it into the calculator, you should get a 0. Therefore, -6 is a 0. But then for part B, it says use the sum and product of zeros to find the other two zeros. So given that it's a cubic, we know there has to be maximum 3 roots or 3 zeros to that polynomial. So I should be saying, I should be labeling first. So I'll say let the other 2 zeros be alpha and beta. So then the 3 roots will be alpha, beta, and -6. If you add them, the sum of zeros is meant to be b on a. Sorry, negative b on a. And if you look at the cubic polynomial, my b is -4, my a is 1. So we know that the sum has to be +4. So alpha plus beta minus 6. Meaning that alpha plus beta has to be 10. And then also using the product of zeros, I'll do it here. I know that alpha times beta times -6 has to be negative d on a. Negative d on a. And that's -126. So dividing by -6, I know alpha times beta has to be +21. And see how we get two simple equations in terms of alpha and beta? We can use them to find the other two zeros. So I can say 1, 2. I can rearrange 2 perhaps as 21 on alpha. Sub into 1. Then you get alpha plus 21 on alpha is equal to 10. Solve the quadratic. This one's easy to factorize. So I get 2 solutions for alpha, but if you actually sub that into equation number 2, you'll see that beta is 7 and 3, and they're sort of just reflections of each other. So it doesn't matter what's alpha and what's beta. I know that the 2 zeros are meant to be 3 and a 7. So I can say, therefore, zeros are 3 and 7. So see how I didn't have to necessarily use long division, use the factor theorem or whatever to find the other two zeros? The benefit of using sum and product of zeros is that sometimes it reduces the algebraic steps significantly. Okay, let's try these examples. So we are using the sum and product of roots identities to find some more complicated expressions. So you can pause the screen here to try the questions, or you can just follow along with me. Okay, for question 1a, it's just a sum of zeros. So I know it has to be negative b on a, which is 4. For the product of zeros, it's meant to be c on a, so it's just 2. Now, using these two identities, you can actually do the rest of the questions. For example, for part D, I don't know what 1 on alpha is, I don't know what 1 on beta is, but I can actually manipulate this expression in terms of this and this, so that we can make use of those identities. For example, if you collect these two fractions together, we get beta plus alpha over alpha plus beta. And notice how this fraction is consisting of the two identities we've just found. So I know exactly what this is. This is just 4 over 2, which is 2. So sometimes you need to manipulate the expression to the expressions that we already know the values of to substitute and finally evaluate. Same thing with f. Have a look at f. It's got alpha squared plus beta squared. Now, I don't know what alpha and beta are separately, but I know I can manipulate it so that I add plus 2 alpha beta. Now, I don't want to just change the expression, so we want to subtract 2 alpha beta. Can you guess why I've added 2 alpha beta? It's because I know that these three expressions together will make a perfect square of alpha plus beta squared. And why did I want it in that form? It's because I already know the value of alpha plus beta and alpha times beta. So the point all comes down to manipulating it so it becomes the expression becomes in terms of alpha plus beta and or alpha times beta. So I know alpha plus beta was 4 and alpha times beta was 2. So we will get 16 minus 4, which is 12. So I didn't even have to find alpha and beta separately. We could use sum and product of zeros to find these values. Let's have a look at G. Similar thing, if I see addition of two fractions, I immediately think about combining them together. So I'll get alpha squared plus beta squared on alpha beta. Now the top expression is already what I've seen in F, and we already know that this expression is 12. So I can make use of that. I know it's 12 on 2, which is 6. And then for question I, 2 brackets. I'm thinking of expanding them together. So alpha beta plus alpha on beta plus beta on alpha plus 1 on alpha beta. Now that expression I know. That expression I know from the previous question. That was actually the answer for part G, wasn't it? It's 6. And I already know what that is. So it's 2 plus 6 plus 1 on 2. And that is just 8.5. So sometimes your previous parts are going to help you answer the next parts. So for question 2, you can try it in your own time. I will probably... You should be able to search these answers on Cambridge. So you can either do that, or if you send me an email, I can send you the solutions. I'll send you a screenshot. Example 3, last example for this lesson. It says the polynomial px has zeros at -2 and 4. Use the sum of zeros to find the other zero. So same thing as the previous example, but I think you can use either the sum or the product. Let's go with the sum. So I'm going to say let the other zero be alpha. Then I know that alpha plus the other roots must be -b on a. So that's alpha plus 2 is equal to 5 on 2. Move it to the other side. I know alpha is half. Easy solution. Part B. Suppose that x minus 3 and x plus 1 are factors. Use the product of zeros to find the other factor of p of x. Well, given that x minus 3 and x plus 1 are the factors, I already know that the zeros are 3 and -1. And then let's call the third one that we don't know as alpha. Then I can see, the question tells us to use the product. So I can see that the product of all the zeros must be -d on a, which is -4, right? Negative 3 alpha is equal to negative 4. So then it's going to be alpha is equal to positive 4 on 3. Find the other factor though. It doesn't say find the other zero, so I should probably say it as I should probably say it's equal to x minus 4 on 3. I'm trying to think whether it has to be 3x minus 4. Or would it be the same thing? As long as it's divisible, as long as it's divisible, I don't think there's an issue with it. So yeah, sometimes you can use sum of zeros, sometimes you can use product of zeros, but if the question specifies, you're gonna have to use that method. And that's it for the examples. So, yeah, there you go. This one, you are going to do Maths in Focus as well. So you just have to attempt the questions attached in the worksheet below. Just choose some questions. Don't do every single question because there's quite a lot. And you can always check your answers down the bottom of the page. So let me know if you have any questions. And good luck with the work. I will see you guys in the next video. Bye!